Hello friends, welcome to my channel once again. Today in this video I am going to share with you some interesting information concerning algebraic and transcendental numbers. Our notations are quite standard and will denote the set of natural numbers, Q denotes the set of rational numbers, R denotes the set of real numbers, C denotes the set of complex numbers. First we start with some standard definition. An infinite set A is said to be countable if there exists a bijection between A and N. That is, if the elements of A can be arranged in the form of a sequence A1, A2, A3 and so on. Otherwise, A is said to be uncountable. By an algebraic number, we mean a complex number that satisfies a non-zero polynomial with rational coefficients. Thus, if alpha is a complex number, then it is called algebraic number if for some non-zero polynomial fx with rational coefficients, f alpha is equal to 0. That means alpha satisfies fx. Every rational number alpha is an algebraic number because it satisfies the non-zero polynomial x minus alpha, which obviously has rational coefficients 1 and minus alpha. Square root of 2 is an algebraic number since it satisfies the polynomial x square minus 2, which is also in Qx. This complex number I, which is square root of minus 1, is an algebraic number because it satisfies the polynomial x square plus 1. If n is a natural number and m is an integer positive or negative, then all the nth roots of m are also algebraic numbers because all these roots satisfies the polynomial x to the power n minus m, which is a polynomial having rational coefficients. So all the nth roots of m are algebraic numbers. The set of all algebraic numbers forms a subfield of C. This actually follows from a much stronger result from the theory of field extensions, that the algebraic numbers forms a field, in fact subfield of C. Therefore, if alpha and beta are two algebraic numbers, then their sum and difference, product, quotient, if beta is non-zero, all are algebraic numbers. It is well known that the real numbers pi, which is the circumference diameter ratio, and the number e, which is the base of natural logarithm, are not algebraic numbers. These are not algebraic numbers, okay? These are not algebraic numbers. Of course, their proof that these are not algebraic numbers is quite deep. So, for obvious reasons, it is not included here. It is beyond the scope of this video. Thus, summing up whatever we have seen so far, if script A denotes the set of all algebraic numbers, then script A is a proper subfield of C because this E and pi are in C, but they are not in A. So this is a proper subfield of C, such that rational numbers are proper subset of real algebraic numbers, but neither the set of real numbers is a subset of algebraic numbers, nor all the algebraic numbers are real numbers. Okay, neither all the real numbers are algebraic, nor all the algebraic numbers are real. Elements of the set this complement C minus A are called transcendental numbers. This means that transcendental numbers are precisely those complex numbers which are not algebraic numbers. Okay. Therefore, as mentioned above, These numbers pi and e, these are transcendental numbers because they are not algebraic numbers. So also are the numbers alpha plus e, alpha e for all algebraic numbers alpha, since A is a field. So, for example, if this is not transcendental, then it is algebraic. So, this minus alpha is also algebraic. So, pi turns out to be algebraic contradiction. So, in this way, all these are transcendental numbers. Question is, how many more transcendental numbers are there? An answer to the above question is given by the following result, which we plan to prove now. The result is that the set of all algebraic numbers forms a countable set. One can then say that the set C minus A is uncountable. So also the set R minus A, because A is countable, R is uncountable, C is uncountable. So these two are uncountable. In other words, we can say that there exist uncountable many transcendental numbers even among the real numbers. So pi and e are two real numbers which are transcendental, but apart from these two, there are uncountable many real numbers which are transcendental. Forget about complex numbers which are transcendental. Okay. To prove the countability of the set A of all algebraic numbers, we need the following well-known fact. What is the fact? A countable union of countable or finite sets is always countable. A countable union of countable or finite sets is always countable. In other words, if n is a finite or a countable set for each n in n, for if for each natural number n is a finite or a countable set, then this union is also a countable set. This can be proved by applying Cantor's method as follows. First, write the elements of A1 like this, elements of A2 like this, elements of A3 like this, elements of A4 like this, and then arrange these elements in the form of a sequence like this. First A1 1, then write A2 1, then A1 2, then 1 3, A2 2 like this, then A1 5 like this. Okay. Here, for example, if any of these AIs are finite set, for example, say A2 is a finite set having just two elements, these are absent, then while forming this sequence, one can jump from A3 to straight to A14, just omit this and go there because these are all absent. So we can go straight from here, then go to this A15 and then again come to A33. We can again jump this, okay, because this is absent, so we can straight away come here. So in this way, a sequence can be formed using all these elements. In particular, if the set A is countable, then this product A times A is also a countable set. This is done like this. If A is countable, then we can write A in the form of a sequence, and then we can define a set AN consisting of all ordered pairs whose first coordinate is AN fixed. This is singleton AN. So first coordinate is fixed AN, and the second coordinate is an element of A. So second coordinate runs through these elements. Then this set is in one-to-one correspondence with A because first coordinate is fixed. Therefore, since A is countable, AN is also countable. And note that A square is actually union of all these ANs. So this is a countable union of countable sets, so A square is countable. So similarly, using induction, one can show that A to the power n, which is A times A n times, A cross A n times, this is also a countable set for every n in n. In particular, for each n, the product q to the power n is countable. This is also q cross q cross q n times. Next, we show that the set of all polynomials over q is a countable set. For each n, let us write an to denote the set of all polynomials over Q of degree at most n. Okay. That is, each an consists of the polynomials of the form a0, a1, a2, x square, an, x to the power n, where these are rational numbers. This is a polynomial degree at most n because this an may be 0 also. Clearly, this qx is equal to union of these ans. If you collect all these ans, take the union, then you will get whole of qx. Note that for each n, these polynomials, these are elements of an, they can be mapped to this n plus 1 tuple, and then this mapping defines a bijection between an and q to the power n plus 1. So, in this way an becomes countable because q to the power n plus 1 is countable. Therefore, each an is a countable set. Hence, it follows that qx being the countable union of these ans is a countable set. So, this set of all polynomials with rational coefficients is a countable set. Now, by the fundamental theorem of algebra, every polynomial of degree greater than or equal to 1 with complex coefficients can be factored as c times x minus r1 into x minus r2 into and so on up to x minus rn for some complex number c, r1, r2, rn. Okay. Fundamental theorem of algebra says that every polynomial with complex coefficients has a root in C. So, it can be applied repeatedly to get this factorization. So, it means that every polynomial of degree greater than 1 having complex coefficients has all its roots in C, and number of roots counting multiplicity equals the degree of the polynomial. Okay. So, in particular, it follows that if AF denotes the set of all roots in C of a polynomial fx which is non-zero in Qx, then AF is a finite set. In fact, number of elements in F is less than or equal to degree of fx. So, F, since we have written it as a set, so that means it counts the distinct roots of F. So, total number of roots counting multiplicity is equal to degree. So, if you count the distinct roots, then obviously it will be less than or equal to degree of x. And if it is fx is a non-zero constant polynomial, then of course it will not have any root. So, it will be 0 in any case, this number of root will be 0. But anyway, it will be less than the degree of fx, less than or equal to the degree of fx. Note that this set of algebraic numbers equals this union, because any algebraic number is a root of some polynomial, some non-zero polynomial. So, any algebraic number belongs to f for some f, non-zero fx in qx, and any root of a polynomial is automatically algebraic. By definition, it is algebraic. So, this A is equal to this union, and this union is a countable union of finite set because each AF is a finite set. Okay. We have seen that each AF is a finite set, the size is less than or equal to the degree of fx, and this qx is a countable set. So, it is a countable union of finite set, hence this is countable. So, A is countable. So, in this way our plan has been accomplished. Proof of transcendentality is a very difficult task, yet quite a few numbers have been shown to be transcendental so far. However, pi and e are undoubtedly the most popular among all the transcendental numbers found so far. Okay. Following numbers are transcendental. So, here we give a list. This list is not exhaustive. Only a few numbers I have listed here. For example, e to the power pi into pi root n. This root over n is in the same level as pi. So, exponent power is pi into root over n. E to the power pi into root n. Okay, root n is above in the same level as pi. So, in the power. So these are transcendental for all n in n. Then e to the power any algebraic non-zero algebraic number is transcendental. These are have been proved. Of course, proofs are quite deep. A to the power b, where a and b are algebraic numbers, a is different from 0 and 1, and b is a irrational number. This is also transcendental. So in particular, 2 to the power root 2, 2 to the power square root of 2 is transcendental. There are other transcendental numbers also, but these are, I thought these are at least simple ones. One can easily understand the meaning of these numbers. Others I am not listing here. And again, I say proofs are very difficult, quite deep. And surprisingly, the following numbers are not known whether they are transcendental or even irrational. What are these? The product of E and pi, it is not known whether this is a rational number or an irrational number, algebraic number or transcendental number. Similarly, pi plus e, pi minus e, pi to the pi by e, pi to the power pi, e to the power e, and pi to the power e. Remember, e to the power pi is transcendental, but pi to the power e is unknown. It is not known whether it is transcendental or even irrational, rational. Okay. So that's all in this video. Uh, Hope you have enjoyed it. If you have liked the video, please subscribe my channel. Thanks for watching.